In this example, we're going to look at a simulation of a simple dynamics of a random walk. Um, this is an idealization of how a polymer in solution might move around. So the model is as follows. Imagine that we have a polymer, which is a sequence of identical monomers strung together in a linear way, and the configuration of it, well, in an actual polymer, what you might have is, for example, if you had polyethylene, so you'd have a CH2 here, and a CH2 here, and so forth. And each one of these bonds is a dihedral angle on it, and can be, roughly speaking, chosen to be either trans or gauche. So trans meaning planar like that, or gauche plus or gauche minus, which is a rotation of 120 degrees around this bond. A simpler version of that, and if you make these rotations, I should say, if you make enough of them, then this straight, say, alkane chain then becomes, on a large scale, a random walk. So a simple generalization of that is a freely jointed chain in which we retain the idea that the distance between successive monomers or beads is fixed, but now the vector from this bead to the next one can go anywhere on the unit sphere, even on top of the old one, and then the vector after this one, can go anywhere on this unit sphere, say there, and these are all supposed to be the same length, and then the vector from this one to the next one can be, anywhere out there, and so forth. So you make a random walk by some succession of choices of the direction of the next bond. So the dynamics for changing this thing once you've made it, how could it move without sort of falling apart again? Well, by the wiggling of these different beads, but subject to the constraint of the fixed length between them. So the very simplest thing that you could do to change the position of just one of these beads would be to make what's called a pivot move. So this bead here, for example, with two of its friend beads fixed, can swing around in a circle that comes by rotating around this axis, this bead. And you see that preserves these lengths here and doesn't touch any of the rest of the structure. And there's nothing here about beads avoiding each other. There's no self-avoidance in this model. So we don't worry about that. So then, to simulate a polymer moving with this pivot algorithm, we would, well, of course we would build an initial configuration of the chain, which we might do just by constructing a random walk as a starting point, for instance. And then after that, what we would do is choose a bead at random and choose a pivot angle at random from 0 to 2 pi, and then pivot the bead and continue. Now, if you had chosen the end bead, this doesn't make any sense. There's no neighbor over here to pivot. So in the special case where you choose the end bead, we could say that we just simply re-choose its direction from its neighbor. In other words, we just freely choose. If we choose this bead as the one we're going to move, and we back up to here, we go out on this unit sphere here, and we just pick a new direction, and that's the new location of this bead. So that is the algorithm, and that's what we want to implement in Mathematica. So the first thing we're going to need is a way of generating random unit vectors. We encountered this in an earlier example, and I'm just going to type out the answer that we came up with at that point. That was one in which we were rotating the cloud of data points around a random direction. And just to briefly recap how this works, it's easy to generate a random vector somewhere in the unit cube minus 1 to 1 in x, y, and z. And then what you do is you ask whether the vector you generated sits inside the unit sphere, and if it does, you keep it and normalize it and throw it out onto the unit sphere's shell, and then you've chosen it without bias as to its direction. If it's outside the unit sphere, it could be somewhere in one of the corners of the unit cube, and you can't keep it because you'll tend, if you did that, you'll tend to point more toward the corners of the cube than you do other places on the unit sphere. So that's the way this random unit vector thing works. As I said before, we need to initialize the path, and the path here is going to be held in a list of positions that we call, I don't know, path. But right now what we need is a function that generates a path, and we need to tell it how many steps we want to generate. And so first what we do is we generate the steps, that is the displacements between the successive beads, and so that's going to be a table of these random unit vectors, of which we need n minus 1 of them. Or actually I seem to have made the thing have n steps and n plus 1 beads in my notes, so let's just stick with that and make it be n steps, n plus 1 beads. And then we need to add those up, and it turns out a nice way to do that is to use fold list. So you use fold list with the function being plus, the starting point being 0, 0, 0, and the successive parameters added up will be steps. So let me just illustrate how that works. So remember that fold list had the behavior like this. We used this in a previous example in the one about calculating the coexistence curve. It's perfect for taking a function and applying it to the previous answer with a new parameter. Well, so in this case what you've got here is the function is adding. The previous thing is the total up to now, and the new parameter is the thing you're about to add. So here's the initial value, 0, the first parameter added on, the second parameter added on to the previous result, the third parameter added on to the previous result. So that's exactly how we're going to generate the path, as being the sum of the random steps that we generated. And that completes our init path function. Okay. We need something to draw the path with, which we're going to call show walk. And that'll take a list of points called points. And here I'm going to check to make sure it's a list. Which is just good practice to worry about the form of the argument that you have. And I'm going to do a little thing here to find the reasonable range to draw the thing in. And then I want to map point onto the whole list of points, and so that will give me a list of function point, and then I need some lines that go from every point to every other point. So first I make a table of pairs of the point positions from the ith to the ith plus first point. And that list needs to stop at the n minus first point, since I'm taking the going to the n to I plus first point would then take me off the page if I didn't stop there. And then I need to put my plot range in there someplace. Okay, so let's see. Let's test this. Okay, so there's our initial random walk in there. You can see the path and the beads and so forth. All that business about finding the maxes and the mins was just trying to get this thing into a box where I can see it, but it won't run off the edge of the box. So now we come to the part where we do the pivot algorithm for changing the path. And we're going to just make one change. So we have a function called pivot, and it will take the points again as its argument. And so usually when we're doing anything complicated enough, we're going to need a module, so we just start typing the function, module, and you've got your list of local variables, which when you've got everything working, you fill that in. But when you do that, you won't have access to them anymore. So I've left these blank, actually, even though I should have put max and min and so forth in there to protect them from the outside world, because if something was messed up, then I'd be able to, with that list empty, be able to ask what were the values of those things so that I could see maybe where the trouble was coming from. Okay, so turns out we're going to need access to the length of the list several times, so let's just get it. The idea is going to be that we create a new list of points, which will be slightly different than the old list by the changing of one value. So let's make a copy in order to have something to change. I need to find a position of the point I want to move, and that I'll do by choosing a random integer from 1 to length. So that's the starting point. I'll just make myself a little comment out here. And then remember I had that special case that I had to deal with about whether or not the point number was the first one or the last one, and in which case we do something special. So if the point is the first one, then what we want to do is change the first position in new points to be the second position plus a random unit vector. And likewise, if the point that we happen to choose is the last one, then what we want to do is likewise to change the last point to be the last minus one point, which is its neighbor, plus a random unit vector. But otherwise, so the way that which works is it goes through these different tests, and if this test works, then it does this thing, and if this test works, then it does this thing, and then if this test works, then it always will, because it's true. So it works its way down through the test. So true is the general case, that is, not np of 1, not np of the last point, but in general, what we want to do is first choose an origin to rotate around, which will be the point we're trying to move, -1. Okay. Then we construct the vector that we're going to rotate around, which is a vector between my next neighbor along the path and my previous neighbor along the path. I then choose a random angle to rotate around, to rotate by. And then I construct a rotation matrix, which is rotating by that theta around that vector. And then I construct the position of the NP point, the point I'm trying to move. I construct its position by rotating the thing with respect to the origin, which means subtracting the origin, applying the rotation matrix, and then adding the origin back again. And that then changes the new points array in just one place. And then what I do for my function to close is I just echo back new points, and that is the thing that the function returns. So now I would like to make a little movie of how this works. Maybe first I should also test to see whether the function just blows up if I do anything silly. So I'll just try, see whether or not it works. Oh. Yes, so this construction here is to check to see whether an argument has a certain property, and I wanted to make sure that the argument of that function was a list, and likewise I'd like to make sure that this one is a list. Okay, so now pivot works. At least it provides me with a list of points anyway. That seems right. And so now what I want to do is I want to make a movie of the chain moving in this dynamics. And so the way I'm going to do that is, first of all, to save the previous path So I initialize the path. I'm going to make basically a function called path, and its integer arguments are going to be saved paths. So the very first thing I do is I start it out like that, and then I make a table I'm going to type this out and then explain what it does. Okay, so while this is running, what this table does here, inside here is this thing called nest. And what does nest do? Nest nests a function onto an argument a number of times. So nest of pivot onto old path 500 times, what that does is computes pivot of pivot of pivot of pivot of 500 times of old path. In other words, it does 500 pivots on old path. Because every time you compute pivot of something, it produces a new path, which then becomes the argument to pivot, and so forth. So what this does is 500 pivots. We then save that in path of I, and so that's going to produce a list of paths in the end, and the old path value gets saved, and then the next time the table computes another value, that becomes the starting point for the next nest. So what all that does for you is saves a path every 500 pivots and does that 20 times. So then I can make some plots of those, and I'll give those plots names. So that's just going to make me 20 plots, all saved in fig of I. And then there's this lovely little thing called list animate, where if you have a list of figures, it will let you see them like a flipbook. Takes a little minute for that to set up. And so we're watching the path as it deforms under the action of these pivot moves. And since we've done 500 pivot moves between one picture and the next, the picture is rather jerky. If we were to do fewer pivots and more pictures, I'm not sure how long this will take to do, but we'll find out in a minute. That part's going to be relatively quick. The slow part is going to be making all these pictures. Let's just see. Well, that wasn't too bad. Alright, how about this? So what I'm hoping will happen is that the paths will then look less jerky because fewer changes will have been made between one and the next, and yet it will cover something like the same amount of total changing of the polymer. So the movie should be less jerky. And indeed now you can see a movie which looks a little bit more continuous. So that gives the idea of how you can program another kind of simulation, random walk dynamics with a pivot algorithm. And again, the heart of the simulation is quite simple. It's just this one pivot step here where you pick a random point to do the pivot on. You consider special cases. Is it either end? If it isn't, then you just simply find the origin on which to pivot, compute the vector around which you rotate, choose a random angle by which to rotate, construct the rotation matrix, and do the rotation, and thereby generate a slightly changed path. So that's the pivot algorithm in Mathematica.